very much for coming. Today I'm going to talk about some equivalence results about tensile streaming algorithms and linear sketches. This is a recent joint work with two amazing undergrad students, Chen Jiang from MIT and also Yichen Liu from Tsinghua. Okay, so first, what are the tensile streaming algorithms? So what is tensile streaming? So this is a framework in streaming algorithms that captures the insertion and deletion of items. So typically it is phrased as follows, as the following problem. So we like to maintain a vector z in x in n dimensions with integer coordinates under a stream of updates. So each item in the stream is one update to this vector by either incrementing one coordinate I by one or maybe decremented by one. And after the sequence of updates to this vector x, at the end of the stream, we would like to compute some function f of x at the end of the stream. And at the during this process, we would like to use space that is much smaller than storing the vector x explicitly, and even much smaller than the dimension of x. And ideally, we would like to have space that's log n, point log n, or maybe square root of n. Okay, so what are some examples of problems that people study in this tensile stream? Tensile, it captures a very wide class of problems. So one, I guess, important example, class of examples is to compute the statistics of the frequency vector. So what I mean, you imagine that we have a stream of items from a universe of size n. We can insert an item at one time, or maybe we can delete one item at a time. And then this vector x, we can view it as the frequency vector of how many times each item has occurred. So one insertion corresponds to increment the ith coordinate, and deletion corresponds to decrement. And then at the end of the stream, we ask some question about the frequency vector, for example, to approximate what is the second moment, or how many distinct elements are there in the final stream, or maybe to output what is an element that has a significantly large occurrence, a heavy bit. So, and this is this model of tensile streaming is a bit more flexible than the standard insertion only stream, because, for example, this allows us to analyze statistics about the difference of two streams. Like we can add one and subtract the other. Okay, and one other big class of applications of tensile streaming is the dynamic graph streaming problems. So imagine that we have maybe a graph initially that is empty, and over the course of the stream, we may insert and delete edges. And then at the end of the stream, we have a final graph, and we would like to compute some graph property, like whether the graph is connected, or whether it's bipartite, or what is approximate to max matching, and so on. And to fit in this framework, we distribute this frequency vector, this vector x, as the frequency vector of how many times an edge has occurred, the indicator vector of the edges. And insert and deletion of the edges, this corresponds to updating this vector x. And then at the end of the stream, this vector x exactly encodes what the final graph is, and then we want to compute some function of this graph. So there are many important problems that people care about and make very efficient, space-efficient algorithms in this framework. So how do we, in general, design a tensile streaming algorithm? So it turns out that most tensile streaming algorithms are based on linear sketches. So tensile streaming algorithms are typically linear sketches. So what is a linear sketch? So roughly speaking, the linear sketch is that we first fix some matrix A called the sketching matrix, and then the streaming algorithm will maintain this vector AX, this sketch AX. So think of A as a matrix with very few rows, but with like n columns. So it's a wide matrix. In this way, maintaining AX takes much less space than storing X itself. So space is much less than n words, and also it's very easy to update. This is because, for example, if you want to update the ith coordinate of x, we just add the corresponding ith column of A to the sketch. So for any matrix A, such a linear sketch can be maintained under these tensile updates. So normally, then the question reduces to finding a good A, or maybe a distribution of A of these sketching matrices, such that knowing the sketch AX is sufficient to recover whatever we want to compute. And most of the tensile streaming algorithms are designed in this way. And turns out that for the problems that people are interested in, there exists distributions of these scattering matrices with very few rows. So the space usage is small. And given that tensile streaming algorithms are mostly linear sketches, so this naturally raises the question: is linear sketching the only approach to tensile streaming problems? So do we have other approaches or other ideas to ways to design algorithms for tensile streaming problems? So it turns out that in general, the answer is yes to this question. All linear sketching is the only approach to tensile streaming problems. And Nguyen and Woodruff showed that if we have a tensile streaming algorithm with the S bits of space, then we can simulate such a streaming algorithm using a linear sketch with about the same space, but provided that the stream may be arbitrarily long. So this means that if we have a tensile streaming algorithm with S bits, but this algorithm is correct on an arbitrarily long stream, maybe their proof needs that the length of the stream to be like doubly exponential at least. Then if we are given such a tensile streaming algorithm, then we can turn it into a linear sketch with about the same space. So one thing to note here is that you may wonder if the stream is doubly exponentially long, then the numbers in the coefficients may be in the coordinates may be too large to even track one coordinate. But I guess their result guarantees that the stream may be arbitrarily long, but at the end of the stream, the final frequency vector has polynomially bounded coefficients. And then as long as the tensile streaming algorithm can handle such streams with arbitrarily long, but the final frequency vector has bounded entries with S bits of space, then we can simulate this by basically linear sketching the same space.
Is it not usual that you would normally think about the space complexity of your streaming algorithm as a function of n, or as a I don't know,
as a
okay, is this so is this like almost a meaningless result? How is this normally interpreted?
So you should think that the final state of the streaming algorithm has bounded entries. So this is a case where the linear sketches can actually handle, because you can always store linear sketches mod like a large polynomial. So the number may go over to some very large number in the middle, but if we mod everything by a large polynomial, then it still solves the problem. And in this case, it's saying that this is basically the only thing.
Okay.
Yeah, but this assumption that the stream may be
doubly exponentially long is a strange edge case example.
Say again?
But we should probably think of it as a very strange edge case example.
Yeah, depending on how you think the length of the stream. Yeah, right. Yeah, but definitely this assumption is not very satisfying. Okay, so then what about the more realistic regime where we have a shorter stream? And it turns out that in general, the answer is no when the stream is very short. So a work by Kallaugher and Price showed that if the stream has only linear length in the dimension of the frequency vector, then there is a exponential separation. So they construct an example where for linear sketches you need enter some constants number of rows, but there's a tensile streaming algorithm that uses log space, maybe polylog space. And I guess the tensile streaming algorithm uses ideas from insertion-only streams, and somehow it has a guarantee that every item in the stream, whether or not it's an insertion or deletion, incurs some small additive error. So as long as the stream is not too long, the accumulated additive error is still accepted. But somehow the separation is only for linear length stream. So there's a big gap between these two answers. So I guess the natural question is that what happens to the I guess one of the most common regime where we have a polynomial length stream. And this is the question that we study in this work. And our main theorem answers the question, said that the answer is yes. I guess less informally, what we prove is that, okay, let's think D, let's fix a parameter D, think this some polynomial, and then we have another parameter R, which is a larger polynomial. Then suppose that we have a turnstile streaming algorithm computing some function on a stream of length at most this larger polynomial with high probability. Then we can turn it into a linear sketch computing the same function for every vector of norm less than the smaller polynomial high probability. And also the sketching matrix has all of S rows, and the linear sketch uses S logs as bits of space. So there's a small gap of log S when we turn the turnstile streaming algorithm into the linear sketch. Okay. So up to this polynomial factor from the length of stream to the norm of the final frequency vector, we can turn any streaming algorithm into a linear sketch.
Sorry, I think I'm still having trouble understanding the parameterization here. Like, how are we thinking of S as a function of n?
S can be anything.
So S is an arbitrary function of n?
Yes.
Okay. And there's just no extra dependence on, there's actually no added anything going on. Okay.
Yeah, okay, maybe the only additive thing is this with high probability. In some regimes, we may lose one over poly and error.
Okay.
Okay, so I guess this theorem is stated for the exact computation of some function f, but just for simplicity for this talk, we will focus on this regime. But the same statement also holds for approximating some parameter or maybe promise problems or search problems. And we also prove another version of theorem for specifically approximating smooth functions f under some definition of smooth. And in that case, we can actually obtain tight results for smooth functions. We can have a linear sketch with S over log R rows, where R is, I guess, it's poly n, S over log n rows, and of S bits of space. Let me just mention that why we have O of S rows here and S over log R rows. I guess in principle, if we have a arbitrary function that you want to compute, then maybe the linear sketch maintains some linear sketch over F2. So every row of the sketching matrix only requires one bit to store. So if we have an S-bit tensile streaming algorithm, which by itself is a linear sketch over F2, then we cannot hope to get better than S rows in general. But then if we are approximating a smooth function, which means like if we add a little bit of noise to the stream vector, the final frequency vector x, the result doesn't change by more than epsilon. In that case, it doesn't make sense for the algorithm to maintain anything over a small field because adding a noise will just give something random. And in that case, we can actually capture the proof actually captures this and can get a linear sketch with S over log n. Okay. And in general, proving lower bounds for linear sketches is I guess it's an easier task than proving general streaming lower bounds because you have more structures in how the algorithm works. So there are some problems and also other problems in some parameter regimes. The strongest lower bound for the problem is only for linear sketches. And then given that we have these equivalence results and combining the two, we also get some new streaming lower bounds for LPR estimation in some parameter lists and also operator norm estimation, eigenvalue approximation, and some other problems. Okay, so in the rest of the remaining time, I would like to go over some high-level proof overview, but before that, any questions? Okay, so So let's first look at the setup of this product. So the goal is that we're given a turnstile streaming algorithm. We like to extract from this algorithm the behavior of the algorithm, a sketching matrix, such that AX can determine the value that turnstile streaming algorithm is computing the probability. So in general, this turnstile streaming algorithm may be maintaining some linear sketch on its own, and may also have some nonlinear parts. But intuitively, the nonlinear part should not be really helpful because for tensile streaming algorithms, tensile streams, it's possible that maybe we insert something at the beginning and do a bunch of things in the middle, and then maybe subtract whatever we insert at the beginning exactly. So the algorithm somehow needs to realize that we need to cancel these two, the insertion and deletion. And maybe also like the stream, maybe like we are adding a random vector, maybe positive or negative, and then we add another random vector, positive or negative, and repeat it many times. And there's a lot of cancellation going on. So somehow, like the hope is to say that the nonlinear part of the algorithm is not really useful to handle these cancellations. This is exactly the type of streams that we analyze the algorithm on and hope to filter out all the nonlinear part of the algorithm. Okay, so more formally, we're going to look at the stream of the following form. We first update the frequency vector with random n-dimensional Gaussians m times independently. So each of these xi, we sample it from a discrete Gaussian in n dimensions of radius r. So it's some very large random vector. R is a large polynomial. So I think each block here is not one update, but it's like a block of updates that will increment the frequency vector by exactly this x1, x2, so on. So x1 is a large random vector, x2 is another large random vector, and so on. We do this a total of m times independently for a very large poly M. And hopefully, like if the stream algorithm is not linear, then it will be confused at this time after these random updates. Then we will do another final update to land at a specific vector y, so that we can make sure the streaming algorithm is actually computing the right function. So the final vector y is final update A is simply the target value y minus the sum of the previous random vectors. Okay, so we will analyze such streams. So how do we do this? So the idea is that we'll mostly focus on the first part of the stream, where we do these random updates, and then analyze the behavior of the streaming algorithm on these random updates. So let's consider the memory states between the adjacent random xi's. So after the first update, we have a memory state of sigma 1, and then we have sigma 2, sigma 3, and up to sigma m. So we're going to fix one such memory state sequence, sigma 1 up to sigma m. And then let's look at the conditional distribution of these random Gaussians conditioned on these memory states. Okay, so then what do we have? Xi in this case, it becomes all possible vectors that are consistent with the transition from sigma I minus 1 to sigma I, right? So this is some distribution, and because of the Markov property of the streaming algorithm, these random Gaussian noise Xi remain independent even if we condition the sequence of the states. And this conditional distribution of Xi's condition on the sequence of memory states is what we are going to analyze carefully. And so I just gave them a name. Mu I is a distribution of Xi conditional on sigma. And then because they're independent, so the distribution of the sum is just the convolution. And then we're going to show later that how to extract a matrix A from these distributions. Okay, but before that, I'm going to claim that what's the goal of this extraction of the matrix that will correctly compute F in this framework. So the goal is that I claim that it suffices to find a sketching matrix A such that for every vector that is in the kernel of A with relatively small norm, here D is the norm that we would like the linear sketch to work, this distribution U, which is the distribution of the sum of these xi's, is approximately translate invariant. So we can move in the direction of U, and the distribution is the same. It doesn't change much. Okay, the claim is that it suffices to find such a matrix A that with this plot. Okay, so why is that? Okay, let's say we fix the sigma and condition on the sigma. And then in order, after processing these random updates up to sigma m, the final update, in order to land at y, the distribution of the final update is y minus u, right? So conditional on the memory states, we have the distribution u, which is the sum, and then the distribution of the final update is y minus u. Okay, so ultimately we would like to show that by sketching the frequency vector by A, we should be able to recover the correct answer f of x or f of y. Then what this means that if A cannot distinguish two final vectors, y1, y2, then y1, y2 better have the same output. Then in this case, that is fine. We just output whatever the common value. So what does this mean for A to not distinguish y1, y2? It's like A y1 is equal to A y2, which means the difference is in the kernel of A. Then in this case, if we have an A such that this is true, then the final update here has a closed distribution in these two cases. So in one case, it's y1 minus mu. In the other case, it's y2 minus mu. So it's two different translations of the distribution minus mu, and the difference of the translation is just y1 minus y2. And if we plug in this y1 minus y2 into this claim, then we know that the behavior of the final update has a very similar distribution. And then because the streaming algorithm behaves closely up to this point, behaves exactly the same up to this point with the same sequence of memory states, then if the final update also have a similar distribution, then the streaming algorithm must behave also similarly after the final update. In one case, it lands at y1, in the other case, it will land at y2. So the algorithm will, if the algorithm is correct, then I guess f should have the same value in these two cases. Okay, so now the goal is that we like to analyze the distributions such that we would like to basically put everything that is such that the mu is not translated invariant into the rows of A, such that the only confusion the streaming algorithm can have is harmless. So maybe as a quick warm up to see why this is true, if the algorithm is actually completely nonlinear. Let's think about, just for intuition, let's think about the case where if the streaming algorithm is just doing something random, it sees a random noise xi and it goes to a random state and so on. In this case, we like to ideally say that we don't really need to maintain anything in A, it automatically have this translation invariance. This is true because in this case, if the streaming algorithm does random updates, then conditional memory states, this xi, the conditional distribution is going to be basically the discrete Gaussian restricted to some random large support. Now, in this case, intuitively, if we believe high-dimensional central limit theorem holds for such distributions, which it does, then we should have that the sum of these distributions is something close to a discrete Gaussian of a larger radius r squared of m. And if it's a discrete Gaussian, it's actually discrete Gaussian, then this distribution is insensitive to any small shifts, as long as the length of the shift is less than the ratio. So in this case, it's consistent with the intuition that we don't really need to store anything to sketch in this case. If this random algorithm can solve the problem, then the problem has to be true. Okay. Then okay, let's see what are the challenges for general streaming problems. So Okay, so one case is that, let's say, these distributions xi, the conditional distributions, let's say maybe each one of them is supported on a small subspace. Okay, it's the same small subspace W. Then the support of the sum must also lie in the same small subspace as well, right? So in this case, if the shift vector U is not in the same subspace, then the distribution is not shift invariant. They have even just disjoint support. So what this means that the sketching matrix A must capture everything that is in the orthogonal complement of the subspace to force anything in the kernel to be in the vector to be in the subspace so that this doesn't happen. And I guess more generally, a tricky case could be maybe these distributions are supported on a lattice, let's say on even vectors. Then in this case, if we sum up these mu i's, then u is also supported on even vectors. Then if we shift in a direction that is odd vector, then again they're going to have disjoint support, so it's not translating invariant. And in this case, what we would like the sketching matrix to do is to include this all1 vector as its rho, so that anything that is in kernel have u1 up to sum from u1 to un equal to 0. In particular, u would be an even vector. And it turns out that generally these two types of situations can be handled by Fourier analysis. It's a good tool to for this I guess in this case, and we will show that the right thing to do turns out to be we look at the Fourier transform of the distribution mu and look at what are the I guess the vectors psi that has a large Fourier regress, and then include those vectors. So I guess the next few slides are probably going to be the technical slides of this talk, where I'm going to demonstrate the proof structure. Okay, I'm trying to make things as simple as possible. So for this, just to demonstrate proof structure, so let's think about the case where the simplest case where the algorithm stores nothing. Okay, so which is the case that each of the mu I is just the discrete Gaussian itself, and then see like how our proof works. This very simple. Okay, so let's first define the Fourier transform. I guess there are a few different ways depending on where we put the constants 2 pi and also minus I. So the version that we use here is the one we I guess we sum over everything the support of the distribution times each to 2 pi I the inner product. So because 2 pi is put in here, so the I guess the Fourier transform is periodic with period 1 in every basic expression, in every coordinate. So okay, I think that this variable psi vector is from the n-dimensional torus. And also to note here that when mu is a distribution, this Fourier transform is bounded by 1 term. Okay. Then in the next few slides, there are 3 points that I wanted to make. So first, I would like to say that in this case, when h mu I is a discrete Gaussian, then the Fourier mass of this distribution, discrete Gaussian, is concentrated around 0, around the origin. And next, I would like to argue that if we have some distribution where the Fourier mass is concentrated around 0, then it implies that the it's approximately translate invariant in the L2 sense. In other words, the okay, I here I guess I changed notation slightly just to make things look okay in when we do Fourier analysis. So mu sub u is the translate the distribution, and we will argue that if the distribution has a Fourier mass concentrated around 0, then the L2 distance must be bound. And ideally, next, what we should do is to apply Cauchy-Schwarz to translate the bound on L2 to L1, the TVD. But it turns out that we need to do it in a careful way that directly applying Cauchy-Schwarz will not give us a non-trivial value. Okay. So first, if we have a discrete Gaussian gamma R, then the Fourier transform is very similar to the Fourier transform of the actual Gaussian, the continuous Gaussian. It has basically the same form. I guess the only difference being that it's now periodic. So this norm here is actually the norm on the torus, which means it's the distance to the closest integer point. And because once we have this form, I guess we know that the Fourier transform value is basically negligible when psi is like 1 over r far from the origin. It's going to be exponential. And then if we have a sum of these m things, its Fourier mass is going to be even more concentrated because it's going to be raised to the power of m. If we have m independent things, the Fourier is just to the power of n. And in this case, I guess whenever this vector psi has norm more than 1 over r square root of m, the Fourier mass becomes negative. So it's very, very concentrated around the origin. Otherwise, other points can just forget about it. Okay. So let's say if we have such a distribution that has very concentrated Fourier coefficients, then it is we're going to show it's almost translate invariant because we can also write down the Fourier transform of the translate distribution in terms of the distribution, in terms of Fourier transform of U itself. So it turns out that by just expanding definition, we have this. It's pointwise multiplied by e to the 2 pi I psi, where U is the direction of the translation. Okay, now if we take the difference in the Fourier domain, it gives us this difference, which is a Fourier transform of the difference of these two distributions. And the claim here is that this is a very small value pointwise. Okay, why? Because if psi is large, then the first term is already. If psi is small, then this inner product here is small. So the second term here is actually close to 0 as well. So for large psi, the first term is small. For small psi, the second term can be bounded by basically this inner product here, which is the norm product of norm. But we know the first one is bounded by 1 over r root m. The second factor is bounded by r to the point 1. So it's some smaller. And then because it's pointwise small, we can give a bound on the L2 of the difference of the Fourier transform. And then by placebo, this gives us a bound on the L2 distance. Okay, let me pause here for 1 minute.
Few slides ago, you said that mu1 to mu1 will be independent, even conditional sigma.
Yes.
But sigma depends on the Gaussian.
Yes, sigma depends on the Gaussian. So sigma is a function of the of xi, but I guess what we are looking here is that we look at the posterior distribution of the Gaussian conditioned on the memory states. Then, because of the Markov property, they're going to be independent. That's it.
So when you say sigma, do you mean like sigma only up to the first I states?
We mean the entire sequence sigma. So I imagine that is the sequence of memory states. Let's say you condition on one particular sequence of memory states and look at what's the posterior distribution of x1, x2, x3, and so on, conditioned on this particular sequence. Now each one of them is a distribution. Okay, I guess it's true that this mu i's can depend on sigma because sigma is a random variable itself. But once you fix sigma, these mu i's are fixed distributions, and then I guess the x i's are independent. Okay. Okay, so here we have a bound on the L2 if we have a concentration on the Fourier norm, Fourier transform. then it turns out that a global application just directly Cauchy-Schwarz on this L2 does not give a good bound on the L1. So I'm not going to show exactly why, but the intuition is just because, like, so how do we convert L2 to L1 using Cauchy-Schwarz? We're applying one function as the pointwise squared value of the function, the other one as the indicator vector of the support, and then we apply Cauchy-Schwarz to get the geometric sum of geometric mean. And then Cauchy-Schwarz is tight or nearly tight if the ratio of these two functions are close, are constant everywhere, almost everywhere. Then this is not the case for discrete Gaussian mu, or the difference. This is because in high dimensions, the discrete Gaussian can take very different values within its effective support. The value of the probabilities can even differ by something exponential. So Cauchy-Schwarz directly applied on the effective support is very loose. So what we are going to do is to actually redo the analysis and apply Cauchy-Schwarz on every line parallel to the shift direction. So if we have we just decompose the support into many lines such that each line is in the direction of u, and then we're going to analyze like what is the L1 distance of these two distributions restricted to this line, and then it turns out that that will be fine. I guess more formally, if we define this function to be the restriction of my distribution on this line, okay, so we start from some arbitrary point and then go in other directions. I guess in the direction of u in other directions, and then we're going to bound the TVD, the 1D restriction of both distribution on this. So I guess at first glance, it may be a harder question, because if we apply the same approach to use the Fourier analysis to bound the L2 distance and then to the Cauchy-Schwarz, we lose the nice property that mu is a convolution of many independent distributions. I guess here it's restricted to one line. But fortunately, the Fourier transform of this f on one line can be written as the integral of the Fourier transform of mu multiplied by some factor over some hyperplane. I guess the exact formulation here is not important. The important thing here is one, if we would like to compute one Fourier coefficient, value of a Fourier transform, it is an integral over a hyperplane that is orthogonal to the shift direction u. So this is a hyperplane orthogonal to u. And the second important point is that this hyperplane basically maps 0 to 0. So we know that the original Fourier transform of this distribution mu is very concentrated around 0. So this means that if we apply this, we can show that this Fourier transform of f must also be concentrated around 0, because it's I guess it's an integral over a hyperplane where if it's xi is 0, then zeta is also 0. So this allows us to say that this 1D Fourier transform of f is very concentrated around 0. Then we can apply the same argument as before to argue that then if we shift to f in this 1D direction, then there's an L2 distance bound between f and ft and ft plus 1. Then we apply Cauchy-Schwarz on this 1D restriction, will give us actually a good TDD bound. And then we'll sum over all possible lines the TV distance between the distribution on these different restrictions. And turns out that will give them. Yeah, so I guess the difference being the behavior of the Gaussian in 1D and in high dimensions. If you think about the Gaussian in 1D, the effective support is actually basically the radius times something, maybe some constant. The things outside, you can raise them. So like within this effective support, the ratio between the largest probability and the smallest probability is a constant. But in high dimension, it's not true. You can show that if the radius is r, you can go beyond a little bit to maybe r plus root r, r plus r times like 1 plus 1 over root n or something, so that the probability can actually differ by something like exponential in this r. Yeah, it's a slightly wider, so that the probability actually drops a lot, because if you look at the I guess the high dimensional ball, most of mass are actually concentrated on the boundary. So like there are much more points on the boundary that even though they have a lower probability for each individually, they still sum up to something. Okay. So far, what have we done? So I guess we showed this simple case. If we start with the streaming algorithm that stores nothing, then we show that we can simulate it using a linear sketch that stores nothing. But hopefully, I guess this proof can generalize and give some more intuitions about how we prove the general theorem. I guess the main thing is just on this slide. So let's see, like, what are the places that we actually use the fact that mu is a discrete Gaussian. So this step is the only place that we use the property of mu. It's that we want the distribution, the Fourier mass of mu to be concentrated around 0, so that the Fourier mass of this function on restrict to this line is also concentrated around 0. But I guess the second thing is the only thing that we really want that if we look at any direction u that is consistent with that is in the kernel, wants that the Fourier transform restricts to this line to have its Fourier mass concentrated around 0. And then the Fourier mass is just the integral of everything that is orthogonal to this shift direction. Right? So it's in the hyperplane that is orthogonal to this direction u. So what this means is that, okay, so now we have this very arbitrary distribution u, and the Fourier mass may not be concentrated around 0, but it can be somewhere else. And the hope here is that we're going to put a few vectors into this matrix A so that we restrict what this vector u can be. And once you fix the vector u, what we want is that everything that has a high Fourier value must be in the hyperplane that is orthogonal to this vector u. In that case, when we shift it with the same analysis, everything will be projected to 0. Okay, so what this means is that we would like to extract a sketching matrix so that we can, by collecting the row vectors to be the vectors psi with high Fourier mass, so that everything with high Fourier mass is concentrated around the span of these rows. Okay? If that is the case, then whenever we look at a shift vector u, and then when we come to this analysis on this function f, which is the orthogonal hyperplane orthogonal to u, it will contain basically everything that has a large Fourier mass. So I guess the final goal is just to find a matrix A such that it collects all the high Fourier coefficients. Okay. So here maybe let me intuitively say what does it mean to have a high Fourier coefficient, and hopefully that will make the next slide one step. So, okay, let's consider one particular psi that has a high Fourier coefficient, and because it's a product, so each one of the factors must also have a high Fourier value at this point. And what does this mean? It means that my distribution must be very aligned with this Fourier base function, right? So because the maximum value it can achieve is 1, there shouldn't be much cancellations. And what is this Fourier base function? It's some function that is periodic in the direction of psi. Okay, so maybe one example is, let's say maybe my function, my distribution satisfies that for this particular Fourier value at 1/3 and 0 elsewhere, it has a very large Fourier value. Then what this means that most of the weights of this distribution must have the same inner product with this psi mod 1. In particular, it means that it must have the same x1 mod 3. Because now this Fourier base function, it is periodic in the direction of the first coordinate, and the period is exactly 3. So if we have a lot of mass on x1 equal to 1 mod 3 and also a lot of mass on x1 equal to 2 mod 3, then there will be a cancellation happen. So what this means is that basically this corresponds to the case that the streaming algorithm actually stores the linear measurement, which is the first coordinate mod 3. Okay, so if we have a linear measurement, if the streaming algorithm stores something like this, then there will be a large Fourier coefficient around this one. And maybe another case is that, okay, so what happens if this is a large Fourier coefficient, then we can apply the same argument to say that now the period is like 1/epsilon for some very small epsilon. Then if that's already more than the radius of all the vectors that we care about, effectively, we would like to say that basically everything in the support should have the same x1 plus 2x2. So this is I guess this is equivalent to saying the streaming algorithm actually stores the linear measurement x1 plus 2x. And then because we have these independent copies, so the final Fourier coefficient is large, means that everyone is large. So this means that the algorithm is actually consistently tracking the same linear measurement. Okay, so next, I guess in the last 2 slides, I'll show you how to exactly extract A. So I guess one thing to note here is that if we are given a streaming algorithm with a very little space, S space, then there are only 2 S different memory states sigma I. And if we condition on this xi being consistent in transitioning from sigma I to sigma I plus 1, then for a typical sigma, we know that the distribution is basically pointwise bounded by the Gaussian up to a factor of 2 squares. And for simplicity, let's also assume that everything is the same. Okay, so the way we construct this sketching matrix is probably just simple. It's just greedy. Like we would like to collect everything, all the Fourier values that are close to 1. We just greedily put the vectors into the rows of A until everything is collected in this pattern. So we start with the empty matrix, and then as long as there exists some psi with Fourier value close to 1, and the psi is far from the previous rows we have added, then we basically add this psi to A. But we need to round it to something like 1/r polygon so that we can actually use this A as a sketching matrix, such that every actually uses log n bits at most. So we run this large Fourier value psi, and then we add it as a row, add to A as well. And then we keep doing this until everything has been included in the span. And so by construction, this already satisfies the condition that everything that has large Fourier value, it is close to it is near the span. So I guess the last thing to show is intuitively why this sketching matrix has only very few rows. Ideally, I would like to say it has only 12 S rows. So the intuition here is that every time we have a large psi, kind of this means that we are imposing a linear constraint on what this support of mu can be, right? So if psi has a large constraint, linear constraint, if psi is large, then most of the things in mu should be very aligned with the base function, Fourier basis function of psi. So this means that this inner product between psi and x mod 1 should take very close values. And every time we add a row, we have one such linear constraint on how this distribution mu could look like. And the other condition saying that the psi is far from the previous span kind of means that these linear constraints are nearly independent. So everyone imposes a linear constraint, and which would reduce the support size by some factor, and these are linear independent. So if we have sum of rows, then the intersection must be exponentially small in the number of rows. But if we start with discrete Gaussian and impose that many different constraints, eventually, if we impose too many constraints, then it cannot be pointwise bounded by just that. So number of rows has to be bounded. This is intuition. Okay, I guess I will skip this slide. So I guess the naive way that one gives S log space, but if we run it carefully, instead of running to like 1 over poly-n, we run it to the nearest values point for a small k, then we can get S log S space. And I guess the open question is that now we still have a gap of log S in this reduction. So can we turn any S-bit streaming algorithm into a linear sketch that also uses all of S-bit space? And also here, we require the initial turnstile streaming algorithm to work on a large poly length stream. And then the linear sketch that we get will work on vectors with a smaller rule. So currently there's a gap of like to the power of 9 or something. So how small can we make this gap? And this may also have some connections to bounded dilution streams. And I guess one general question is that, okay, this is for general turnstile streaming. Can we prove any other structural results beyond this? Okay. Yes.
I read the results much easier if somehow if adding and removing an element does nothing, and if you have no time component or something, or is that how you get the two to the S result? If you assume that it's not just the same, it's literally the same state.
Oh, yeah. So I guess the 2 to something that's proved by like repeatedly applying some sequence operations that goes back to the initial state, the sum up to 0, and then somehow in this case you view your algorithm as a Markov chain, and then this 2 to something is the time that you require this Markov chain to mix, and somehow I guess maybe something similar to.
So if you try to avoid talking about Fourier by just talking about almost commuting operators, you get stream length.
Yes, I guess once it mixes, then I guess it goes back, kind of goes back to steady state.
But for that, you need to have enough time to not
Right.
be able to store a clock, because otherwise you can just store everything about the diagonal.
Yeah.
And to